Hi, all. Now we can have a discussion about the crystal structure, which is the topic in solid state physics. So the plan is we have a set of questions. Some of them are previous questions for net, and some of them for gate and just etc. So we'll discuss the questions one by one, and the theory of the respective questions will be discussed at that moment itself. Okay, so first question is very simple question. If R is the radius of the atom in a crystal with BC structure, then the lattice parameter A is given by. Okay, so first of all, we should know what is my lattice parameter. So the lattice parameter is in case of the BCC structure. The BC structure is like this. The body is center cubic system. So the side of the cube is basically called the lattice parameter. So in cubic, basically we have three types of lattices: simple cubic, the body centered cubic, and face centered cubic. So in body centered cubic, we have atom at the locations of all corners of this cube, and as well as there will be an atom at the center of the cube. Okay. Now we have to connect the lattice parameter and the radius of the atom. Okay, so you have to view it is three-dimensionally. So if you draw the atom at the location of all these dots, so this would be the figure. Almost the figure would be like this. Okay, so the atom at the corner and the center would be in contact, and the atom at the corners may not be in contact. So this would be the pattern of the body centered cubic system. But if you are going for a simple cubic, when you're going for simple cubic system, in the case of simple cubic, the atoms are present only at the corners. So I have drawn only one face of the cube now. And if you draw the atom, okay, so sorry, it should be some that side. Okay, so if you draw the atoms, then the atoms at the corners would be in contact. Okay, so that is for simple cubic. But for body centered cubic, it may not be the case. The atom at the center of the body and the corner would be in contact. So then it is easy to find the connection between the radius of the atom and as well as the lattice parameter. So if you take this body diagonal, if you take the body diagonal, so the body diagonal would be equal to root 3 times A, and that would be equal to how many radius? 1, 2, 3, 4 radius. So that would be equal to 4R. So actually, this atom and body center atom and the atom behind this corner, so this would be in contact. So root 3A equal to 4R, and therefore A equal to 4R by root 3. So the correct answer for this question is the option B. A is equal to 4R by root 3. Okay, so this is not a previous question. So I just introduced this question only to introduce the relation between the lattice parameter and radius. Okay, now what would be the relation between lattice parameter and radius for simple cubic system? So in the case of simple cubic, the atom at the adjacent corners would be in contact. So therefore, the lattice parameter would be equal to the twice of radius. And what about face centered cubic system? Again, for face centered cubic system, if you just draw the single face, then the atoms are present at the corners of the face and as well as at the center of the face. Now, if you draw the bigger picture for the atom, okay, so then the atoms at the corner and at the phase center would be in contact. So this is the phase diagonal. So phase diagonal is written as root 2 times the lattice parameter. Root 2a is equal to 4r. So therefore a is equal to 4r by root 2. Okay, so that's all about the question number 1, and we have discussed all 3 different variations of the first question. Okay, so is that, if that is clear, then we can move to the second question. Okay, so the second question is the previous question. It's a question asked in NET 2018. The hard disk of radius capital R are arranged in a two-dimensional triangular lattice. What is the fractional area occupied by the disk in the closest possible packing? The NET 2018 question. So hard disk of radius R arranged in a two-dimensional triangular lattice. So can you consider a triangular lattice? So the atoms are present. Oh, sorry, hard disk is present at the corners of this disk. Okay, so here we have to find the fractional area. So then first of all, we have to know what is by fractional area. So fractional area by definition, it is the area occupied by the disk within the triangle which is a triangular lattice divided by area of the triangle. Okay. So now the thing is the how much area is occupied within the how much area of the disk is occupied within the triangle. So that we can easily found out, because if you look at here, only this much area of the first disk is inside the triangle. Here this much area is inside, and here this much area is inside. So if it is an equilateral triangle, then angle 60. So that means 1 by 6 of single disk is inside the triangle. So then we have 3 such disks. So therefore the area occupied by the disk within the triangle would be 3 times of 1 by 6 times of the area of circle divided by area of triangle. Okay, so if R is the radius of the disk, then the area of the circle or area of the okay, circle, or it is basically disk. The area of the circle we can write as pi r square. Now what about the area of the triangle? Now suppose if the side is A, if the side is A, then say this side would also be A, so equilateral triangle. Then the area of the triangle would be is equal to half times A cross A will be A square sine 60, and that would be equal to root 3 by 4 A square. So how we have found this area of the triangle? So remember, if you have a triangle with one of its side is vector A, the other side is vector B, then the area is given by half of modulus of A cross B, because A cross B gives the area of the parallelogram with sides A and B. Its half would give the area of the triangle with sides A and B. So half, what is the modulus of A cross B? It is length of A, the length of B, the sine of angle between them. Okay, so here both sides are A and the angle is 60 degree. So that is why I have written half A square sine 60, and that is equal to root 3 by 4 A square. So this is a way we can find the area of any triangle. Okay, so therefore now finally we will go to the definition for fractional area. So the fractional area is equal to 3 times 1 by 6. The area of the disk is pi r square divided by root 3 by 4 A square. Okay, so this I have written here. Now what is the relation between R and A? So if you look at this figure, we can directly write A is equal to 2R, and therefore this become 3 into 1 by 6 would be 1 by 2 pi R square root 3 by 4, and we have A is equal to R square, so that will be 4R square. This R square cancels, 4 cancels, so we have pi divided by 2 root 3. That is the answer. The fractional area occupied by the disk in a triangular lattice is pi upon 2 by root 3. So do we have that answer? So pi upon 2 by root 3. If you look at here, there is no direct answer, but this option A is actually this. Because if you multiply this with root 3, it become pi uh, root 3. No, okay. I made a mistake. It is pi upon 2 root 3. So it would be pi root 3 divided by 2 root 3 times root 3. So root 3 times root 3 would be 3. So we have pi root 3 by 6. The option A is correct. So pi root 3 by 6. Okay. So that is the answer for the fractional area occupied by the disk. So remember, the question number 2 is based on a two-dimensional lattice. Actually, this question can be extended to three-dimensional lattice as well. But in three-dimensional lattice, instead of fractional area, the question would be the fractional volume or the packing fraction or packing factor. So in case of 3D lattices, for 3D lattice, we define packing fraction is equal to the volume of the atoms occupied in the lattice divided by volume of the lattice. For example, if you have a simple cubic system, the atoms are present only at the corners. Only at the corners. Now, the how much the volume is inside for each atom. Okay, so if you look at carefully, only 1 by 8 of an atom would be inside the symbol cubic, and we have 8 such atoms. So 1 by 8 into 8 times the volume of one atom. So it can be 4 by 3 pi r cube divided by the volume of the lattice is a cube. So 1 by 8 and 8 cancels. We have 4 by 3 pi r cube divided by a cube, and here a is actually equal to 2r. So therefore it becomes 4 by 3 pi r cube divided by 8 r cube. R cube cancels. So we have 4 by 8. 4 by 8 is 2. So it becomes pi by 6. So pi by 6 is the packing fraction or packing factor, or the packing efficiency is also called packing efficiencies. Usually packing efficiency is written in terms of percentage. Okay, so will divide it by 100 and we'll write this much percentage. Okay, so that's all about the packing fraction, packing factor, or the fractional volume, etc. Okay, so this kind of questions can also come. So we can stop it here. So we'll discuss the other questions in the next video.